Hi everyone, welcome back. We're glad to have you. Today we speak with Director of Product Marketing, Mark Forbes, about the history of IC development and how that directly has impacted you and will continue to impact you and your design practices. I have a passion for capturing some of the history so you know why you do things that you may have not known happened 30 years ago. You're really going to enjoy this deep dive into what's happened over the last 50 years and how it impacts your career every day. Lean in and enjoy. I'll see you on the other side. Welcome to Altium's OnTrack Podcast, where we talk to leaders about PCB design, tackling subjects ranging from schematic capture all the way to the manufacturing floor. I'm your host, Judy Warner. Please listen in every week and subscribe on iTunes, Stitcher, and all your favorite podcast apps. And be sure to check out the show notes at altium.com/podcast, where you can find great resources and multiple ways to connect with us on social media. Well, Mark, thank you so much for joining today. Excited to talk to you and learn about your vast knowledge. That means we're old.
That's exactly what it means.
Really in the industry, but not only PCBs, also ICs and how they've affected design. So thanks for joining. It's fun to have you in the office always, and particularly on the podcast today.
Happy to be here.
So you and I were chatting upstairs about ICs, which you know so much more about than I can even begin to think about, and I always enjoy learning from you. And we were talking about how PCB design over time has been dramatically affected by the trajectory of ICs.
Yes.
Right? And so I thought I'd bring you in today and just, have that conversation out loud, right?
Awesome.
So other people could learn from you as well. So the first thing you and I had talked about was really increased integration. So why don't we just jump off there and just go and tell us about.
Okay. So I basically spent my whole career in electronics, which I love, and it's great. And it's been kind of equally divided between hardware and software, which is somewhat of a unique look. And so the first microprocessor, the commercial microprocessor, came out when I was in college, and it was a big deal for students at the time because you're making a turn in your curriculum. And at that time, the first commercial microprocessor was built by Intel. It was called the 4004, and it was 2,300 transistors, and it was in a 16-pin DIP package. And now the latest microprocessors, the Snapdragon, for example, is in a 1,440 ball gate array, and it has 8.5 billion transistors.
Billion with a B.
Yes.
I don't even know how we design around that kind of density.
From the integrated circuit manufacturing, it is really difficult, but it's only difficult if you look at it like I just described it. We came from here to here. If you look at how we got there, it's a series of innovations in process, and just like printed circuit boards, they were all on phenolic bases at the time.
Right.
And now we've got all these wonderful materials based upon the application.
Right.
So that first microprocessor actually required 3 other chips to run. It needed an external RAM, an external ROM, and a communications controller. They were not integrated. And then as things moved forward, those were integrated onto one chip. And then, for example, that 4004 had 16 I/O ports. Well, there's not a lot you can do.
So what time frame are we talking about?
1971 is when the 4004 came out.
Okay.
So it's ancient history.
I was there.
Yes. And then, of course, the 8080, which was really the microprocessor that exploded the idea that I don't have to design things discretely. I can use this general purpose computer and just program it to do all my functions.
Right.
And it was about 8,000 transistors, and it was on a 40-pin DIP because they realize we need a lot of I/O to control the things we want to control.
Right.
And now the Snapdragon has several hundred I/O, and a lot of them are specific, like USB controllers and Wi-Fi and this and that, and all that stuff was external. And so when you put all that onto one package, you have some problems, obviously, in PCB design that you have to deal with.
Yeah.
You have 1,440 balls in a very, very small space.
That's what I meant when, like, how do you, I mean, just the routing around that many pins, you know, the fan outs.
Right. It's difficult, and it generally increases the number of layers.
Right.
For your escapes.
Right.
And, Charles File, who had been at Altium for a long time, he actually wrote a book on breakout and routing, and when you talk to him, your eyes just start getting bigger because you realize the magnitude of this problem.
Right.
And it's nothing like laying out a board with a 16-pin dip that you can do with tape and, and so forth. So that's the main effect that this increased integration has had on printed circuit board design, is so many functions have been shrunk into a single chip, and now you have to figure out how to get those out to other parts of the board, that, connectors and support chips, and it is a major problem. And
then I imagine there's problems like heat dissipation and
heat is. It's funny. I had showed you a picture of a board, which I think people can download. It was from a television in the late 1960s, and it was pretty much the last vacuum tube, but it was on a printed circuit board.
Yeah.
And you flip it over, and you can see the burn marks from the heat from the vacuum tubes. Now, we don't have to deal with that kind of heat today, but still, you've got more functions in a smaller area. And then something else we wanted to talk about was speed. When they run faster, they run hotter. And cooling is a major problem as well.
Right. So, talk a little bit more about geometry, and then how that passes into speed, and then how that affects the overall design. And people who are listening to this podcast, like, I'm sure they're aware of the troubles they have today, but it's interesting to hear from your perspective, having watched that whole trajectory of where we came from, that it was relatively easy. Like,
yeah, it's steps, it's not a giant leap.
I remember Rick Hartley and Dan Beeker and some others talking about, I think it was in the 80s, early 90s, where they basically said they thought they understood wave theory until they hit this spot. And it was having to do with what you're talking about, because the rise times got so much faster, but they didn't know why. And they said, basically, we could design badly up to that point.
Absolutely.
Right?
We never thought about EMI, RFI back in those days.
Yeah. So talk about all those implications.
Yeah. And so you mentioned geometry, and that is a huge factor in why we were able to integrate more stuff onto the same chip. If the geometry hadn't changed, that BGA would be this big, not this big.
Right.
So, for example, the geometry in 1971 was 10 micrometers, 10 microns. So that means the smallest feature you can have on the IC is 10 microns.
Okay.
On the current Snapdragon chip, it's 7 nanometers. Now let's put that in perspective. If I had a 1,000-page book, say a big dictionary, that's 10 microns. 1/20th of one page is 7 nanometers.
Oh my gosh.
But like we said, it didn't just go like that.
Right.
It went.
Yeah, over time.
It's basically Moore's law, which says you get twice as much it doubles every 2 years.
Right.
And amazingly, that's been almost a linear relationship for all this time. But now we're running up against some physical issues, which is the kind of things you're talking about.
Right.
And we mentioned speed. The original 4004 ran at 740 kilohertz. And the Snapdragon runs at 2.9 gigahertz. And to put that in perspective, if the 4004 is your car and you're going 60 miles an hour, the Snapdragon is going 65 miles per second.
Oh my goodness.
And we mentioned heat. The faster you run, the warmer it gets. But back in the days of early microprocessors, for example, the 8080 ran at 1 megahertz. The 8086, which was the first 16-bit that everyone thought was going to solve every problem in the world because it's so fast, ran at 5 megahertz. So the speed has become important because of, I mentioned earlier, RFI, EMI. Back in the early days, running at 1 megahertz, an antenna is feet long.
Right.
And so none of the traces on the board are going to act as a resonant antenna. So there was no radiated signals. We just designed stuff as it looked good, basically.
Right.
The traces were, of course, very thick. And at that time, the only people who were concerned with frequencies in the gigahertz were folks that were designing radios. And one of the biggest, of course, is Motorola.
Right.
And whenever, when we would get to a point where we couldn't understand what was going on and you kind of had a hunch it was radiation, you'd go to the Bible at the time, which was the Motorola RF Design Guide. And it was mostly talking about, building the design. But then there was a segment on printed circuit board design that no one else had this data. And it was about how do you reduce EMI and how do you bypass things to keep it from radiating. And so that was kind of only used in radio, and now those concepts apply to the vast majority of printed circuit board designs. Because when you're running at 3 gigahertz,
right,
an antenna is about this long,
right,
and there's a lot of traces that are about that long.
Yeah, exactly. Yeah.
But like you said, it wasn't this jump. It was a nice, easy curve.
Right.
And we started running into these things. And like you said, from the other person you interviewed, we were confused. This worked fine.
Yes.
On my previous design, now why is it just garbage?
Not working, right.
And that's when people that had a little bit of radio knowledge said, I think we got a lot of antennas on this board.
Where were you at that time of your career? What were you doing? And what kind of gave you really hold, and I think that's important that we share with today's designers, the history of this, because I think we lose perspective.
Definitely. Right?
And I think it's important that we preserve it. And so what were you doing in those years as some of this, really exponential spiking up was going, and how did that sort of impact you and the people that you knew, and what kind of dynamics did you see going on?
Well, my first job out of college was working on the weapons management system on the F-16 fighter plane, and it used a pair of 8080s. One of them was the active processor, and the other one kept track to make sure that the other one hadn't gone off into space, and if it did, it would take over.
Right.
Our printed out code listing was about a foot thick, and I believe that was probably the most intensive use of an 8080 ever, because it just wasn't that powerful. Right, okay. And so it was really exciting, because about every 2 years there was not just an incremental advance, there was this quantum step. The first 16-bit processor, and then 32, and then 64. And with each of those, the problems multiplied. And I don't want to imply that printed circuit board design in the 70s and 80s was a dropkick, because we were just learning about these problems. Right. Now, we deal with on a daily basis. Right. And so there were surprises. The first circuit board in my collection, I'm quite a geek, that I showed you with the vacuum tubes, there's not a straight line on it. It was all hand-drawn. Yep. And it's a huge board. Yes. And so we started learning about how to pack signals then, and then, oops, I've got coupling between my traces, and now I have to deal with that problem. And then we come up with differential pairs and terminated lines and constant impedances, which is exactly what people did designing radio. And I started getting interested in radio when I was in high school and became a ham radio operator. And so kind of this merge of the speed of the processors and my interest in radio became really interesting, because a lot of people, they could read the rules and say, okay, I can't get these traces as far together, or I've got to use differential pair, but they didn't completely understand why. I see. Mm-hmm. And so when you're running any type of AC signal through a wire, you create a field around it, and if you get another one close and it's got a field, they're going to interact, and you get problems. And the way that we found these things, for the most part, was data errors. So you're running your processor at say 10 megahertz, and now you bump up a new design and you're going 15, and suddenly I'm getting garbage back when I try to read the memory, what's going on. And you look at it and you look at it and you find out, oh, I'm getting an interaction on this, and either the bits are swapped, which is not likely, but they've gone into that undefined area, and it's neither a 1 nor a 0. And now you get garbage out.
Oh, interesting.
And so that was really interesting. Later, I went into basically mass storage and peripherals. And again, everything was trying to go faster, more dense. I don't know if you go back this far, but my first PC had 5 1/4 inch floppy disk that had 178 kilobytes. That was mass storage.
I remember getting a 40 megabyte hard drive, and I thought, what will I ever do with all that storage?
All the information in the world.
Right?
So, similar things. You discovered with mass storage, you've got this big motor. Well, what does a motor generate? A whole lot of fields. And there were lots of design rules that had to be generated to lay out your board, because, you know, you want a disk drive that's this big.
Right.
And so a lot of those boards, if you open up a disk drive, they have a hole in the middle where the spindle is.
Yeah.
They're that compressed. But you've got all these fields and stuff. And so now, you know, digital electronics is easy because it's DC. Well, no, it's not. You've got lots of switching going on.
Right.
And AC electronics is much more difficult to understand. So, again, we're learning, and then the speed increases, and the sizes get smaller. And so, at this point, we are getting near the physical limits that can't be broken. For example, we've gotten to the point where sometimes if you try to locate a memory on a PC board that's too far from the processor, the electrons can't get there in one clock cycle. And so again, how do you find that out? Oops, I've got data errors. Why do I have data errors? So you got to move it back. You can go 3D, get it closer.
Right.
And so we're now fighting the flight time of an electron, which just fascinates the heck out of me.
The flight time of electron, like, that's wild. Tell me about, we were talking yesterday, so teach us about just the silicon die.
Yeah, this was fascinating. So the way integrated circuits are made is like old photography used to be. You have a negative, you shine a light through it onto light-sensitive material, and then you etch away the stuff that was exposed, and you have a circuit or a photograph, darker. So the reason they were using 10-micron geometry is because that's the best they could do with the etching techniques, with the lenses, and so forth. And unlike photography, where you've got a small negative and you're trying to enlarge it,
right,
we're going the other way around. We've got a big negative, and we're trying to make it exceptionally tiny.
Right.
And so as I was reading up on some things, the current stuff, an MOS transistor, the gate of an MOS transistor today on the Snapdragon, for example, is 9/10 of a nanometer. And then the author mentions that's just a bit larger than the width of one silicon atom. And so, again, you can't make it smaller than one atom.
Can you make it smaller than an atom? Like, yeah.
And so you've seen in the last decade a change from two-dimensional ICs into three-dimensional stacking, and a lot of ideas have been tried, some of them not so good, some of them excellent. And really, to improve speed, there's only two things you can do. Number one, more cores. Obviously, we've seen a lot of that.
Right.
And number two is, can I change the geometry to accommodate my physical limits, which is speed of light and the size of an atom. And
that's crazy.
Yeah. And so as we've gone forward in electronic hardware, it's so much synergy. You know, we have advances in printed circuit boards, advances in ICs, advances in the IC manufacturing,
material science, like all kinds of
everything,
chemistry.
And the material science is a good one, because when people think technology, they always think microprocessors and electronics, but materials have come, and batteries. without the kind of batteries we have developed, these handheld projects that are, on a printed circuit board this size couldn't exist.
Right.
Or you'd have 10 minutes of battery life.
Right.
So every couple of years, lenses got better. They found better ways of polishing, eliminating any kind of defect. And the ways that they etch and ways that they make the metal have changed. And you look at a wafer, and years ago there might be 200 or 300.
Yeah.
And now there's maybe 500, but there are 60 times more transistors on it than there was 10 years ago.
That's in 10 years. All this, what amazes me about this whole conversation, as I was just kind of doing the math, and I'm like, we're talking basically, to quote you, like from the caveman days to the limits of physics.
Yes.
Inside of 50 years.
Yes.
Which is
it's
mind-boggling. It's hard. It's wild. It's hard to believe.
Well, you mentioned 50 years, and it's right about the 50th anniversary of the moon landing.
Right.
And they had basically discrete computers. They had a ridiculously small amount of memory. I think it was 256 bytes. And that navigated the LEM from the orbiting spacecraft around the moon to the moon. And I watched a bunch of documentaries, and one of them was so interesting. If you've watched the footage of the last, 10 miles of the descent, they kept getting an error. It came up 1202 and then 1201. Nobody knew what it meant. And they're like, do we have to abort? Can we land? What's going to happen?
Right.
And back in Houston, nobody knows, except in the back room, the woman who had written the code for the errors said, it doesn't matter, go. And the reason was because they were smart enough to write the software that said, if we get too much data, we'll just start ignoring things that aren't important.
Oh, okay.
And it turns out it was an erroneous signal from an antenna. And because it wasn't getting acknowledged, it kept sending it. And every time it sent, I've got an error, it put this 1201 error up.
Oh.
But she knew, because she coded it, that it was going to ignore that because it wasn't as important as keeping these guys flying.
Right.
Yeah. And so, software kind of plays a role in here too, but we're really talking about the hardware. But
doesn't it amaze you that we could do that 50 years ago? I feel like it was like, wire and string. I don't know how we did that 50 years ago. It was really
a lot of brain power.
A lot of math and a lot of brain power.
Yeah. I was talking to one of our engineers, younger engineers this morning, and I said, do you realize that in 1960, we had never launched a rocket that didn't blow up? 9 years later, we're walking on the moon. I look at what's happened with ICs, but those 9 years were just an incredible leap of technology.
Right.
But still, compared to what was going on just 3 years later with Mica Processors, those were antiques.
Yeah, it's fascinating. So, in light of this period of time, what sort of things have you seen kind of maybe in 10-year slots? How this, I imagine there's kind of some leapfrogging, maybe not, where the IC speeds up and we go, oh crap, board design's a problem, or software.
Yes.
And then we got to catch up, and then we get here, and then it's like, it just seems like it would be sort of this leapfrogging. So what impact, since we're obviously, our listeners here are engineers and designers, what impact does this have sort of decade by decade, or, whatever time frame makes sense to you?
During a lot of that time frame, it was passing the buck. So you'd have a system, and you calculate that the throughput is going to be this, and it's not this. And you say, okay, where's the bottleneck? It's you. Your product. It's the printed circuit board, right?
Oh, yeah.
And this went on a lot. And it's, the old joke, is it a hardware problem or a software problem?
Right.
And it's your problem.
Yeah, right.
So I saw a lot of that. This part of the circuit, there was an advance, and now it's way ahead of everything else. And then something else now becomes the bottleneck. And so it's kind of like you said, it was not exactly leapfrogging this,
right,
but little steps ahead.
Yes.
And then you find what the next area is that needs attention.
Right.
And That's has happened. You're talking about 10-year increments, but that happened literally
every 2 years, probably, right?
Sometimes,
or every year,
4 or 5 months, depending upon the technology you're using. And one thing we haven't talked about is there were a lot of false starts. There are a lot of failures in terms of electronic ideas and designs. And some of those were disappointments. We looked at a product which probably no one listening has ever heard of, but it's called bubble memory. And Texas Instruments developed this. At the time, the big bottleneck was non-volatile memory, because when I turned off my computer, everything was lost except what was in the ROM, and that was basically the operating system. So I worked for a company that made electricity meters, and we're trying to record the electricity use over a month. And if you have a power outage, it's gone. So this bubble memory was one attempt at non-volatile memory. When you turned it off, everything stayed there. And it was a convoluted way of doing things that was extremely slow. But for our application, we bought into it. And I remember the day the salesman came in, literally with a tear in his eyes, and said, because I think he'd already been counting his money. And he says, I got bad news. Texas Instruments dropped the project. So we had to go in a different direction. But what was not obvious for a week or two was they dropped it because there was better technology just about ready to break through. And this happens a lot. I did consulting for a number of years, and 3 companies I worked for in a row, before they ever produced and sold the chip, they canned the project because someone else had leapfrogged them, and what they were going to come out with wasn't going to be competitive.
Made them that irrelevant.
And so they just cut the string on it. I mean, millions of dollars of R&D, and they just cut the string. Yeah, it was really, and a couple of the companies are pretty big. One of them was a startup, and they just got too far behind, and they got their funds cut. But it hasn't all been success. It hasn't all been fun. A lot of hard work, a lot of brain power, and people coming up with totally new ideas that worked.
Well, when you were talking about the hand-drawn circuits, not too long ago, Lee Ritchie came in and did some video here, and he brought in a board that actually went up to the moon on Apollo 11 that he designed. And, I think we forget, I want to capture these stories because I could just listen to that guy all day, him and Happy Holden, like them talking about the old days or whatever. When you think about, again, what they did was so little. So he had basically what was a hand-drawn small circuit that he etched in his sink and then turned his sink blue. And then he took it over to his dining room table and he was like drilling holes in it. And his wife was mad because he wrecked the sink and drilled holes in his dining room table. But here he has this board and he goes, yeah, some of these are up on the moon still, I'm like...
And they probably still work.
50 years ago, right? And so it's again stunning what we did with so little, but now all this speed, and then every time we leap forward with the ICs, it directly impacts the board design.
Absolutely.
And how do you keep up with that? Data sheets? How do you?
It's the ongoing engineering education is something that engineers don't think much about when they're in college, but you have to keep up all the time. Trade magazines, online magazines are a really good source because you have people in the industry who are doing these things, writing articles and telling you how they overcame these problems.
Right.
Very important. Manufacturers, when they come out with a new part, they'll often, have seminars, and getting the information directly from the manufacturer is always good. But one thing I've noticed, I started noticing this about 20 years ago, how come there aren't a whole lot of old engineers? And the reason is they don't keep up. I have to work harder today than I did when I was out of school 3 or 4 years, just to keep up with because you could look at it like a funnel, because we're building on what we have in the past, and now we're out here, and you have to know this instead of this.
Well, it's interesting. I was talking to someone here in the office that's on our executive team, and he and I were both talking that because most of us are nerdy around here, and he and I were talking about how we don't understand and how we feel fortunate that just that we've kept up with iPhones, with just using our Google Drive and Microsoft products, like we've kept up because it's been part of our work,
Right.
but we've also been curious. So we've self-educated, but there's people that are in their 50s or 60s where they'll go get a burner phone because they don't want to learn, like, or they find it really challenging. So anyways, we were both saying that we felt lucky that we remained curious and we are a little geeky because it helped us keep our skill set up so we can still be relevant.
No doubt.
Because, if you're in your 50s and 60s, when we look at that 50-year time frame, if you weren't keeping up,
You're driving for Uber.
Yeah, right? You are driving for Uber. It's a good way to put it, right? It's frightening. So, and that's not a pat on my back. It just happened to be the area that I'm interested in, right?
Well, you said something really important, and that's curiosity. And I would guess that the vast majority of engineers select that career because they are curious.
Mm-hmm.
And at some point, I'm sure at some point, everyone loses a lot of that spark.
Yeah.
Some before others. But I was looking at some articles and pictures of the very first IC, which was invented in 1959. And there are a couple of interesting things about it. One of them is, obviously, somebody said, I wonder what would happen if instead of making one transistor on a die, I put 5. Would that work? And they tried it, and it did work. And the other interesting thing is that 4 people actually came up with the same idea at the same time, and the patent was granted because Jack Kilby's application got in before the others. But they were all working on the same thing at the same time, and it just was this spark based upon what they had all seen happen.
Right, right.
That said, I wonder if I can do that. And that's the really thing, is I wonder if I can do this, or I wonder if I can make it smaller. I wonder if I can make it fast.
Right. And usually those things are to solve a problem, like there's a demand to go faster, right? I wonder how we could do that, right? Instead of just going, we can't go that fast, too bad.
I remember, when I was in high school, I grew up in Illinois, and everybody knows what corn is in Illinois. And someone said, I wonder if we can increase the yield. In other words, the number of bushels that they get from each acre. Mm-hmm. And I remember I had a friend, and her parents were farmers. And her mother said to me, if they could do that, they'd be doing it by now. And I thought, wow, is that a backwards way of looking at it? Right. And so about the time I got to high school, the yields on corn were about 100 bushels an acre. And when I went through that 100 bushel ceiling, if you will, it was huge news in the Midwest. So we did a customer success story with my old college roommate, who is still in Illinois, and he owns a farm. And I said to him, well, what's the current yield rate? He said, well, a farmer down the road got 293 bushels per acre last week. And
wow.
I just about fell over. And you know what part of it is? Technology.
Oh.
They're using GPS. They're able to get the rows. So imagine if you've got
I'm going to share that. I'm going to share that success story in the show notes, because you guys that are listening will love to see it. So go on to explain about how the technology.
In the past, at most, they would take a stake and run a string, and that was their straight line that they tried to emulate. And actually, they were pretty good at it. So we start getting these technologies, and someone in agriculture, which a large green tractor maker, said, "Hey, we can improve farming." And so they started with GPS. Well, it wasn't accurate enough. Sometimes you're on an exit from the freeway and you see your little dot is still going up the freeway.
Right.
Well, that doesn't work in a farmer's field.
Right.
So they implemented ground-based augmentation. So the accuracy is less than an inch.
Wow.
And the tractors today can actually drive themselves, but it's not legal. So they have to have someone sitting there. So the GPS enabled them to go straighter, enabled them to go closer together. And then the other thing, which if you watch the success story, you'll see this very vividly, if your field is not rectangular, if you've got another angle here, you lose a lot of space here.
Right.
You either get overlap and the corn doesn't grow well, or there's nothing planted and that doesn't grow very well at all.
Right.
And so now with GPS and with the data that they get from the agricultural department, they're able to run those up and exactly match. And all this combined is plus crossbreeding of the corn. All that combined is what's responsible for this 3-to-1 increase. Goodness. And the weird thing is, if you plot the increase of corn yield and the population of the planet, they almost overlay each other. And so you think, we better keep improving our yields.
Right. That's something else. And it's amazing that technology affects so many areas of our lives, right?
And so many of them that we don't even think about or see.
I was, sometimes when I'm out on a walk or something, and I've been talking to friends who know nothing about PCBs or any of the crazy stuff we do, and I say a circuit board. And I'm like, I was standing on a street corner and I go, let's just look around and I'll tell you where there's some circuit boards around here. If you just stand on any street corner, you've got lights, you've got sensors, you've got signage, you've got cars that are full of, like we are literally surrounded by electronics all the time. It's completely altered the landscape of our lives in 50 years. And just like vertically, right?
Right.
So where are we headed? Do you have any conjecture on, now that we're hitting the limits of physics, like where do we go from here, Mark Forbes?
I believe in 20 years we won't be using electronics. It will be some other light or some other technology. If you look at electronics all the way back to Ben Franklin almost getting electrocuted. So the first products were, if you remember, he had a key in what was called a Leyden jar. That was a battery. Okay? And so we had batteries, and it's like, okay, we have this energy, what can we do with it? And people discovered, I can light something up for a little while, or something like that. And then some of the earliest physicists discovered resistance, capacitance, inductance, how that works. And then somebody discovered, and I don't know how this happened. Actually, I do. They wanted electricity to flow in one direction only, not backwards.
Oh.
And they invented a diode, except it was a vacuum tube.
Oh, okay.
And so it was just two plates, and it was polarized, so the electricity would only flow in one area. So now I've got all these new applications. For example, I can demodulate a radio signal with a diode. And so now, instead of just hearing clicks, Morse code, I can get more intelligence out of that signal because I have this diode. And then somebody said, what if we had another element? And they got up to pentodes, which are 5 elements before. But we had this sudden leap from passive circuits to now active circuits that can do things. Pass signals in one direction, amplify them, mix them together. And that opened up all kinds of things, especially like in radio and then television. And then what we're looking for is a discontinuity. The vacuum tube was a discontinuity. They discover, I'm trying to think who it was, Bardeen and his partner, the transistor. And they saw what was going to happen immediately. They saw, it's on a block of wood this big, but we can make these really small. And then there was another discontinuity. Now you've got radios that were this big that slip in your pocket.
Yeah.
And so the next big discontinuity was Mica Processors. We're no longer worrying about individual transistors and individual gates. Now we've got this huge IC that can do all kinds of things. We just have to tell it what to do. And that's kind of where we're at today.
So you think we're going to have some other fundamental breakthrough
that I do.
Won't involve, again, because we're getting to the end of that, right?
Yeah, and I think like most things, it's going to be a hybrid at first. There'll be some electronics. Right. And I've already seen some of these products. There was a company that was making memory systems for the Department of Defense. And if you have electricity, it radiates. And it might be very, very tiny, but as we have discovered, sometimes it doesn't take but a tiny signal to be detected.
Right.
And so the Department of Defense didn't want anybody to be able to sniff out those signals, so they went to light for the transmission. Light doesn't radiate outside of the tube.
Yep.
And now it's secure.
Yep.
And so these hybrid systems, and every advance kind of starts this way.
Yeah.
Some people say, well, I don't know what I can do with that. And another person says, well, it's great for this really narrow application, but it'll never, but that's what they said about microprocessors.
Right.
In fact, Intel looked at their first microprocessors as a way to sell more memory because they were a memory company. And they weren't yet willing to accept that I could have a whole business selling microprocessors.
Which reminds me of the Altium origin story a little bit, right? That they were, the two guys that started the company, they were developing a desktop plotter. I don't know if you knew that. Dave, I'm forgetting his last name, David, one of our co-founders. Anyways,
this happens when you get older, too.
It does. I'm going to get one of those things by Elon Musk now, the Neuralink, and it's going to poke into my brain so I have perfect recall. But he and his research assistant at the University of Tasmania, they were trying to, because they were doing tape ups, right?
Sure.
So they were getting to the point where you could plot, reduce and plot out film to make circuit boards, and they wanted to make this desktop plotter instead of the big bulky systems, and they were going to sell that sucker for $30,000 and get rich. And at the time, personal computers were coming out, and so Nick Martin said, instead of lifting up and relaying down tape, I bet you I could do a little circuit simulator on these new personal computers. And so they were working so hard on this desktop plotter thing, and someone walked in the office and they said, that's not your product, that is.
That's great.
And that's how they started making design software.
It's also why it's important to have another opinion, because you are down at this level, usually.
It's so true.
And you're not seeing the big picture as well.
Yep.
And you brought up PCs. That's very interesting, too, because that was really the thing that convinced companies, I can have a whole business selling computer chips. And then the product became the PC. I worked for a company that made computer systems, and we had these custom terminals that were stupid expensive. And the customers kept coming to us and said, well, why can't I use my PC? And I thought, we better figure this out because it's going that way. And unfortunately, the company management disagreed. Their business model was, I need this much money per seat, and sometimes it doesn't work that way.
No.
And they eventually went out of business. But so, we started out with the IC, and then we went to the microprocessor, and everybody's like, yeah, there's a few applications for that. And a couple of people looking at it from this said, no, I can build a personal computer. And then I have a personal computer. Now that's the product from which I can do these other things.
Right.
And almost everything in electronics has been that way. A small but great idea gets bigger, and then somebody really exploits it.
Right. It's so interesting. Well, I think we're out of time, but this has been, we could just do this all day long. This is like riffing, So thank you so much for sharing your perspective, because I know so little, and I bet you our listeners the same. Like a lot of us don't know the history of ICs. Well,
as I've gotten older, I feel like part of my obligation is to fill in people so that they know where we came from and the problems we solved, because sometimes you need to go backwards and say, hey, that solution is going to work over here. And if you don't know how we got there, you can't do that.
Exactly. And I think it's really important that we all start telling our stories a little bit, like I said, with Lee Ritchie, with you, with people who have been around in that 50-year period, to tell those stories, because it does inspire younger engineers and designers to jump off maybe some of those ideas, or maybe just appreciate. I mean, can you imagine like coming out of university right now and you have all the tools and the chips that they have now, and just like, like they take it for granted, but it was really an arduous, long haul.
And everybody comes into the movie at a different spot.
Exactly. That's a great way to put it. So I think that I like the idea that maybe younger engineers get to see the movie from the beginning a little bit, right?
But what you said earlier was so important, and that is stay curious. Stay
curious, my friends. It'll make you the most interesting designer in the world. Well, thanks again, Mark. It's been great. We'll do this again. Well, I'm sure we'll find some other rabbit hole to go down. But thanks so much for sharing your history in the industry. And thank you to our audience for joining on today's podcast. Please remember to like, subscribe, and send us your ideas. We love to hear from you. And Altium Live is coming up October 9th through 11th. Please join us. We'd love to have you there. We have a great lineup of keynote speakers. And speaking of being curious, this is a great place to fill up your backpack with lots of great information from industry leaders. So thanks for joining. We'll see you next time. Until then, remember to always stay on track.